Hello everyone, my name is Mohammad Saiful Hassan and I will be giving a short summary on the second module of the course CS351 Artificial Intelligence offered at the Habib University. Throughout Module 2, we were introduced to machine learning, through which we learned about certain classification techniques such as decision trees, naive Bayes, artificial neural networks, um, followed by certain metrics that would evaluate the classifier's performance. Then finally, we learned about clustering using k-means algorithm. So what actually is machine learning? Machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. It focuses on the development of computer programs that can access data and use it to learn for themselves. In this course, we narrowed our focus to supervised and unsupervised ways of machine learning. Now, supervised learning is where you have input variables and output variables, and you can use an algorithm to learn the mapping between the function from the input to the output. In the second module, we really focused on the classification techniques of supervised learning. So now the question arises, what is actually a classification problem? So a classification problem is when the output variable is a category such as a yes or no, or some sort of a result like positive or negative, or it can be any color or any defining characteristic. So now the question arises, how do we illustrate a classification task? As shown in the picture, illustrating a classifier task consists of two parts, induction and deduction. The induction involves the machine learning algorithm to learn a training set of data by extracting certain features, by calculating probabilities, or whatever mechanism the algorithm has to take. And it predicts the output value, basically that's known as the class label. That predicted value is checked against the test set of data, and it is made sure that the predicted value is accurate as possible. The goal of classification is to predict accurate class labels for new or unseen records. As in the given example, a classification technique may be used to predict the winning team for a future game based on the knowledge from previous games. Heading on to our first classification technique, which is the decision trees. A decision tree is a tree-like graph with nodes representing the place where we pick an attribute and ask a question. Edges represents the answer to the question, and the leaves represent the actual output or the class label. As shown in the example on the slide, the tree makes a decision whether to play outside or not based on attributes such as the weather, temperature, humidity, and the wind. Now, one of the most famous characteristic about the decision tree is that it's a greedy strategy because it splits records or attributes based on an attribute test that optimizes a certain criteria, as nodes with homogeneous class distributions are preferred. By homogeneous class distribution, I mean class distributions with lower levels of impurities. These levels of impurities can be measured by two formulas, one being the Gini index and second being the entropy values for a certain class. In this course, we also learned certain metrics that are used to evaluate a certain classification technique's performance. These metrics focus on the predictive capability of our classification model. A confusion matrix, as shown, is usually created in order to compare predicted labels with actual labels. Using the confusion matrix, we can actually calculate the precision, recall, accuracy, or F measure of the certain classification technique. Accuracy, as the name suggests, tells us how accurate our predicted model is, and it is the most widely used metric. The precision tells us how many of our selected items are relevant, which is actually the ratio of our accurate results with our actual results. while the recall tells us how many relevant items are selected, which is a ratio of our actual results with our predicted results. Now, heading on to the second classification technique that we learned in module 2, that is a naive-Bayes classification technique. It is a classification technique based on the Bayes theorem with an assumption of independence among predictors. Using this technique, every pair of features being classified is assumed to be independent of each other. Why? Because it's easy and fast to predict the class of the test data set. Plus, it also performs well on a larger set. With the assumption of independence, these naive-Bayes classifier performs better as compared to other models like logistic regression, and you also require less training data. An example of independence would be that a fruit may be considered to be an apple if it is red, round, and about 3 inches in diameter. But even if these features depend on each other or upon the existence of other features, all of these properties independently contribute to the probability that this fruit is an apple. And that is why it is known as naive. However, there are certain limitations when using this classifier technique. For instance, if a categorical variable has a category was not observed in training data set, then the model will assign a zero probability and will be unable to make a prediction. This is often termed as zero frequency. And in order to solve this, we can use smoothing techniques. One of the simplest smoothing techniques is called the Laplace smoothing or the Laplace estimation. In the part A of our second assignment, we predicted some values for our given problem using our own implementation of the naive-Bayes classification technique. We implemented it using scikit-learn, which is a free machine learning library for Python. It actually focuses on various algorithms like vector machine, random forest, k-neighbors, and it also supports Python numerical and scientific libraries like NumPy and SciPy. Moving on to the third classification technique that we learned in the module 2, which is the artificial neural networks. So a neural network is a machine learning algorithm based on the model of a human neuron. The human brain consists of millions of neurons. It sends and processes signals in the form of electrical and chemical signals. An artificial neural network is an information processing technique. It works like the way the human brain processes information. Artificial neural network includes a large number of connected processing units that work together to process information. They also generate meaningful results from it. These networks usually consist of mimicking neuron, which are information processing units that are actually fundamental to the whole operation of an artificial neural network. They consist of three basic elements: a set of input links, an output, an adder for summing up the input signals weighted by the respective synaptic strengths, and an activation function for limiting the amplitude of the output of a neuron. Moving on, the multi-layer feed-forward networks are one of the most important and the most popular classes of artificial neural networks in real-world applications. They actually use backpropagation algorithms. In these networks, learning is accomplished by modifying network connection weights, while a set of input instances is repeatedly passed through the network. To ensure accurate learning, a mechanism is set in motion, which measures the gradient of the function uh, and compares it with respect to the output value of a certain node, allowing our algorithm to make the decision on whether to propagate back from a node or not. Now, the limitations of the network being that the neural networks perform well with linear and non-linear data, but a common criticism of neural networks would probably be particularly in robotics is that they require a large diversity of training for real-world operation. This is so because any learning machine needs sufficient representative examples in order to capture the underlying structure that allows it to generalize to new cases. Hence, the neural networks can easily be trained to the point of working well on training, but poorly on test data. After learning about supervised learning, we learn about unsupervised learning. It is a form of learning where you have only the input data and we don't have any corresponding output variables. The goal of unsupervised learning is to model the underlying structure or the distribution in the data in order to learn more about the data. Clustering is a form of an unsupervised learning. In clustering, we try to find out homogeneous subgroups within the data such that the data points in each cluster are as similar as possible. According to any similarity measure, that similarity measure could be a Euclidean based distance or a correlation based distance. In our course, we learned about clustering using k-means algorithm. And k-means is an algorithm. It is actually an iterative algorithm that tries to partition the data set into k predefined distinct non-overlapping subgroups, where each data point belongs to only one group. It makes sure that the data points in a cluster are as similar as possible while also keeping the clusters as different as possible. It actually assigns data points to a cluster such that the sum of the squared distance between the data points and the cluster centroid is at the minimum. And the centroid is the arithmetic mean of all the cluster points. So the lesser the variation we have within the clusters, the more homogeneous the data points are within the same cluster. Now there are certain limitations when using this algorithm, as this algorithm will only be applicable when the mean is defined. It's difficult to calculate the mean for categorical data without assigning them a numerical value. Another limitation would be that we need to specify the k, which is the number of clusters in advance. And in case of any outliers, it would negatively affect the distribution of our data in clusters, as certain outliers would result in data to belong to a cluster that it is actually not a part of, given an inaccurate output. With the limitations being said, this marks the end of our module 2. Thank you.